Hello, I'm Zongbo from CWI and QSoft. Today I'm going to talk about the Tolerant testing of stable states with a polynomial gap via generalized uncertainty relation. This is the joint work with Philip and Jonas. So let's start. First, let's define the stable state. First, we have these poly operators I, X, Y, and Z, and then we can define the polygroup Pn as a tensor product of the poly operators with some global phase. Then we define stable states as the joint eigenvectors of S for some maximum abelian poly subgroup S. For example, we only have 6 1-qubit stable states. They are 0 state, 1 state, plus state, minus state, and plus I state, minus I state. Why we care about stable states so much is because they have a lot of applications in quantum computing, such as the quantum error correction, the classical simulation of quantum algorithms, and also stable states. They are very good state design, and you can also use them for benchmarking. So for now, let's talk about the problem of testing stable states, which is you are given copies of psi, the input state, and you want to distinguish whether or not there exists some stable state which has high fidelity with the input state, or for any stable states, they only have low fidelity with your input state. This high and low is stated from the parameter of the problem, epsilon 1 and epsilon 2. They are constant number between 0 and 1. So first, the GNW21 paper, they solved the so-called non-tolerant case, which is they solved the case for the epsilon 1 is 1. Their tester can distinguish whether or not the input state is a stable state or is at least constant far from the stable states. Later in GIKL24, they give a tolerant tester, but it's not fully tolerant, which means that their epsilon 1 can only choose with some constant number larger than some number. You cannot choose epsilon 1 to be arbitrary constant number between 0 and 1. And the relation between the epsilon 1 and epsilon 2 is quite good, it's polynomial related. Later in Srini and Akopol's paper, they prove with a conjecture that you can actually have a tolerant tester with arbitrary epsilon 1, constant number between 0 and 1, but the relation between epsilon 1 and epsilon 2 is not that ideal, it's kind of exponentially related. So in our work, we give a tolerant tester. Here you can choose arbitrary epsilon 1. And also the relation between epsilon 1 and epsilon 2 is a little bit better, it's kind of polynomial related. So after our work, there are two following work. They also have the similar results. So here's the timeline for this 3 work. So first in August, Srini Akopol posted a paper, and in October we have this proof for our work. And we communicate with Srini and Akopol a little bit. They found that actually they already got the proof several months ago. So a few days later, we post our work in archive, but exactly 2 days later, Said and Mehrdad also post another proof for this question. So actually we have 3 different proof, slightly different proof for this question. Okay, for now, let's look into the algorithm a little bit. Our algorithm is the so-called Bell difference sampling, raised in GNW21 paper. This Bell difference sampling takes 6 copies of input psi and output accept or reject with some probability. So our algorithm will be repetitively run this Bell difference sampling to estimate the accept probability, and then output the probability minus 1 over 2 times 2. We call it Q. So let's look into the Bell difference sampling a little bit. First, you take 2 copies of psi to do a Bell sampling. And then you take another 2 copies of psi to do another Bell sampling, and then you XOR the result of two Bell samplings. That's why we call this Bell difference sampling. And once you have the new 2n-bit string, you can have some poly p, and then you measure the 2 copies of psi, measure each according to the eigenspace of p. We call it Weil measurement. And you accept if and only if this 2 Weil measurement has the same result, and you reject otherwise. To understand this algorithm a little bit more, let's take a detour to the linearity test. So in the linearity test, you have a Boolean function f, and you want to say, okay, so what's the distance between this f and all the linear functions? So what you're going to do is that you uniformly randomly choose x and y, and also you calculate x plus y, and then you query this f with these 3 coordinates, x, y, and x plus y. And then you test whether or not these 3 coordinates the function values fulfill the linearity properties. So we already know that the property the f passes this test is related to the distance between the f and the linear functions. So we can also define this probability as the Gauss 2 norm, the U2 norm of f. So this result actually establishes the relation between the U2 norm and the distance with linear functions. Similarly, we can define the U3 norm for f, and we can also argue the U3 norm is kind of related to the distance with quadratic functions. So once you have U3 norm for Boolean functions, you can also define the U3 norm for any quantum state psi. And then, actually, the Bell difference sampling, the output of Bell difference sampling Q is actually a very good estimator for the U3 norm of any quantum state psi. This is the result from Srini and Akopol's paper. And also, we have this factor 2, which is the stable states has some canonical form, which is quite like a quadratic function. So actually, we're going to analyze this algorithm is actually to establish the relation between the U3 norm for the quantum state psi and the distance between the psi and stable states. So this is the question we're going to answer. So to establish the relation between the Q and the stable state fidelity psi, of course, we need an upper bound and another lower bound. So from GIKL23, we already have a good upper bound, polynomial related with degree 6, quite natural because the Bell difference sampling takes 6 copies of psi. And then our goal becomes we want a lower bound as polynomial of Q. If once we have this lower bound, we can conclude that we have a Tolerant tester, and also epsilon 1 and epsilon 2, they're kind of polynomial related. So our result is that we can have a lower bound with some polynomial of Q with degree 100, a very nice number. So how to have this lower bound? First, we use the fact from the GNW paper. They show that to have the lower bound, you only need to find a very, very good abelian polysubgroup V, which has high weight. So our goal now becomes to have some abelian polysubgroup V with high weight. Here the weight is defined as a sum of the square of the trace between the polys and the input state. But how can we find this abelian polysubgroup V? We can find this from the Srini's and Akopol's result. They prove that there exists a not too large V prime, which is a polysubgroup, but maybe it's not abelian, which also has high weight. So our question now becomes, can we find an abelian polysubgroup V from this V prime? And actually, we can answer this question by yes, were generalized uncertainty relation, as suggested in the title. So now let's try to find an abelian polysubgroup from some subgroup with prime with high weight. So first, let's define the anti-commutation graph for this V prime. The vertices of the graph is V prime, and the edge, the P and Q, they have an edge if and only if they anti-commute. So in this graph, we can conclude that if we want to find some abelian part V among this graph, it actually corresponds to the independent set here. So for this graph, we have found V1 and V2, they are independent sets. So V1 is abelian, V2 is also abelian. So you can conclude that the weight of V1 and weight of V2, they're kind of larger than one half of the weight of V prime. So we conclude our first observation is that we can always find the abelian part V with weight at least 1 over the chromatic number of gamma V prime times the weight of V prime. This is our first observation. Our second observation will regarding to the structure of this gamma V prime. We can show that because the V prime is a polysubgroup, so it's actually isotropic to a polygroup with shorter qubits times the abelian part. So this tells us that this graph is actually look like gamma pk for some smaller k, but here each vertices consists a lot of little vertices, but it's always empty graph inside. So from this point of view, we can conclude that the chromatic number of the whole graph is actually equal to 2 to the k plus 1 for some k. So our next observation will be try to establish the relation between the k and the so-called large zeta number, zeta. Large zeta number is defined by SDP for this graph, and also it's kind of related to the other quantities, the independent number of the graph and the chromatic number. So we try to find some idea from this large zeta number. And also here's some examples. For an empty graph, the large zeta number is n, and for the complete graph, the large zeta number is 1. So what's the large zeta number for this very specific graph? We prove that for this graph, the large zeta number is actually smaller than the size of V prime over 2 to k. So we kind of establish the relation between the k, the chromatic number, and the large zeta number. So let's get into the last observation, which is directly from the generalized uncertainty relation here. First, let's look into the uncertainty relation, the old one, which is, suppose you have anti-commuting polys A, then the weight of A is actually smaller than 1. So our generalized uncertainty relation will be, so for arbitrary A, so A doesn't need to be anti-commuting polys, but you can choose arbitrary A. The weight of A is actually smaller than the large zeta number of the anti-commuting graph of A. Why we call this the generalized one? Because if A is anti-commuting polys, the anti-commutation graph will be complete graph with large zeta number 1. With this generalized uncertainty relation, and also we know that the weight of V prime is quite large, we can conclude that we have a lower bound for the large zeta number of the graph. So let's put things together. So first, from the first and second observation, we can conclude that we only need to bound this 2 to k plus 1. And from third and fourth observation, we can conclude that. And also, we need to know that V prime is not too large. It's from Srini and Akopoulos result that we can show that 1 over 2 to the k plus 1 is actually a polynomial of Q. So, combine these two, we can conclude that we have a lower bound, we have a polynomial lower bound with degree of 100 here, which completes the whole proof. So let's talk about the open problems a little bit. So first, because we have a polynomial related, epsilon 1, epsilon 2, but the degree is quite large. So the first open question will be try to optimize the degree. For now, it's 600. And the second question is that our proof is kind of existence proof. It's not constructive. Maybe it's kind of constructive, but we cannot find an algorithm to explicitly have this constant. So second question will be to try to algorithmize the proof. And the third problem is about to extend the result to third layer stable state, which is, we already know that the U3 norm is related to the distance with stable states. So we can naturally ask, can we also prove that the U4 norm is actually related to the state with degree 3, and so on. Here's a reference. And now let's spend 1 minute to talk about why we have this 100 number. It's quite nice. So this 100 number is actually from this 49 plus 51. And the 49 is about the size of V prime, and 51 is about the weight of V prime. First, from this BSG theorem, a theorem from additive combinatorials, but it's a refined version. We have this 6 here. And then from the recent breakthrough, polynomial Freeman-Russell theorem, we have this parameter 8. And then we have the small numbers using probabilistic method. So if you want to improve the 100 a little bit, you really need to open the black box of the combinatorial theorems. Thanks for listening.